nonlinearities, of which we saw two famous examples. One is the Bezier effect, the other is the trapeze effect. The trapeze effect, as we pointed out, is basically an extension twist coupling which is nonlinear. In other words, it depends upon the initial twist as well as the over and above that the additional elastic twist that the beam undergoes. So that affects the torsional stiffness, or in other words, it could be the other way around. What we talked about is an extensional load which affects the torsional stiffness, but again at the same time it could be a twist which affects the extensional stiffness as well, because S12 is basically coupling in either direction. What we will start off with today is to look at how this particular trapeze effect and such other nonlinearities are handled in our framework, perhaps not in terms of the derivation but in terms of the end results of the cross-sectional analysis. So now the trapeze and other nonlinear effects. The trapeze we repeatedly mentioned because it is a very well-known effect and many others have tried to model it, though not in an asymptotically correct manner, at least in some ad hoc fashion. But the other nonlinear effects people have not even bothered to look at, and many of them are equally important to the trapeze effect. So what we mentioned for the trapeze effect will in general hold for the other nonlinear effects as well, as far as the cross-sectional analysis is concerned. So this is based on VAM. When we model it, like linear analysis, even nonlinear analysis, many cases can lead us to closed form analytical solutions for many practically useful problems as well. And that is one way of handling it. The other way, of course, is through numerical analysis, primarily a finite element based solution. So the first way we handle these nonlinear cross-sectional analysis, an example of that is in the 1999 International Journal of Nonlinear Mechanics paper, where we have got closed form analytical solution not only for the trapeze effect but all other nonlinear effects, and there are a huge number of them. None of them have been named based on certain things, and there's a lot more which needs to be explored based on those results. So we have closed form analytical solutions for that. The other situation is where you have much more complex geometries, because this is restricted to strips which are thin rectangular strips, and later has been extended to the closed form analytical solutions have been extended to thin-walled open section beams as well, which are made out of strips, like for example I sections, channel sections, etc., which are also very practically relevant. But once things get much more complex, like an airfoil section and things like that, of course in many of those the trapeze or trapeze-like effects are not very critical because the torsional stiffnesses are fairly large. But you still have thin-walled thin airfoils where the thickness to chord ratio is fairly small, typically of the order of 12% or lesser. So even in such situations, sometimes you really need this kind of an analysis. And many such situations, because of the complex geometry and material distributions involved, we have no choice but to go for a finite element implementation of the same theory. So it's again the asymptotically correct theory, but the end implementation is through finite element analysis. So if you cannot get closed form analytical solutions. So that's how a VABS, software called VABS resulted, which many of you are familiar with, the variation asymptotic beam section analysis. And the person who actually initially brought it about was Carlos Sesnick, but that was a linear code. The nonlinear effects were introduced by another student of Professor Hodges, Bogdan Popescu, and the nonlinearity was introduced for the first time in 1999, and now it's much more capable. But still, only up to cubic terms have been involved here, whereas in this closed form analytical solution that we have, you'll see that we have gone even up to quartic terms, that is basically fourth power. So the first case where we have closed form analytical solutions is for thin rectangular strips with initial twist, and we have done this even with initial curvature as well. But right here I'm just presenting the result for the case where you have only initial twist, no initial curvature. in this particular case, as I said, there are two ways of expressing this cross-sectional nonlinearity. One is by making the stiffness matrix S bar itself functions of the 1D variables. The other is to retain it as constants and then add additional terms more other than quadratic to the one-dimensional strain energy density. So that's basically what is done here. Suppose you didn't have the second term and third term, you had only the first term, that would be a linear cross-sectional analysis, because the way this particular expression is written, the matrix SL, SLN and SN are all consisting of constants. Those constants depend, of course, on the material properties of the composite layups that are involved and or isotropic materials, of course, is a special case. And the geometry itself in terms of the width of the strip, the thickness of the strip, the thickness of each ply in the strip and so on and so forth. So, and of course the location of each ply with respect to each other. So that's the information which goes into that, and because we have been given a particular beam, so all these things are known a priori, and so therefore SL, SLN and SN are determined as numerical values. But the expressions for those are closed form analytical solutions. That's what I mean. Whereas in this case, those SL, SLN, SN, etc. are equivalent ways of expressing the same thing, as we shall see in the next slide, will have to be calculated by a finite element analysis of the cross section. Of course, there is a finite element analysis of the reference curve, which is the 1D analysis, which we have to do later. But even the cross section analysis itself, in the case of complex geometries and material distributions like airfoil sections, have to be done by finite element analysis. In other words, you will discretize the cross section into 2D finite elements, quadrilateral, triangular, whatever you want, the typical way of doing a 2D meshing, and then you basically apply the asymptotically correct solution in order to determine the cross-sectional stiffness coefficients. Whereas in this case, you have actual expressions in terms of those geometric features, in terms of those material properties, and then you can evaluate each one of these matrices. Now, the vectors which are multiplying here, this is epsilon L, which is our standard thing that we basically look at, which is gamma 1, kappa 1, kappa 2, kappa 3, which of course, consistent with the notation that I was talking to you earlier, should actually have bars. So because here it is a thin strip, and in a thin strip, the transverse shear effects, that is basically the contribution to the energy of the transverse shear strains, namely gamma 1 alpha, or what we call as gamma 1 2 and gamma 1 3, are very small. So the whether we take them into account or not, up to the first order approximation doesn't get affected at all. It's the second and higher order approximations which are engineeringly insignificant. So only in such situations you really need to introduce them, because it's thin strip. So now what is more important in a thin strip is the nonlinearities, whereas in a thicker beam the transverse shear effects will come into prominence and the nonlinear effects will go out of prominence. So here the first term basically involves the extensional strain, the twist per unit length, and the two bending curvatures, and basically the cross couplings between them. But because SL is a matrix of constants, basically it's only the linear effects which are present here. But these two additional terms that we have basically couple that epsilon L with an epsilon N, which consists of all quadratic terms. But note that not all quadratic combinations are present. Only those which are asymptotically relevant at that first order are included over here. So what you have is kappa 1 squared, kappa 2 squared, kappa 2 gamma 1 1, kappa 2 kappa 3, and kappa 2 kappa 1 as products. And then because it is going to couple with epsilon L there, this is going to basically interact with this, of course, along with a constant coming from the material properties and the geometry. But what is important to see in this epsilon N vector is that all the terms that are there either have a kappa 1 or a kappa 2 or both. So unless and until kappa 1 and kappa 2 are present, that is basically twist per unit length and bending, which is in this particular direction. If this is a thin strip, so basically its thickness is small compared to the width, and at the same time the width is small compared to the length. So this is an example of a thin strip. So now this can undergo two types of bending. One is about this direction, the other is in this particular direction. In this direction you see that it is very stiff because it has a much larger height, and you know that to take a simple example of an isotropic material, the moment of inertia of relevance is h into b cube, whereas here it is b into h cube. So here, so this is much larger moment of inertia and therefore much larger bending stiffness, as you will observe from common sense. And so you basically see that the kind of curvatures that you can get in this particular direction are very small, whereas the kind of curvatures that you can get in this direction are much larger. So the nonlinearities associated with larger deformations are more prominent compared to the nonlinearities associated with smaller deformations. Again, it's the same case with twist, because this is similar to an open cross section. The torsional stiffness is very low and you can easily twist it, and it can have very large twisting curvatures, or in other words twist per unit length. And so therefore, if and only if kappa 1 and kappa 2 or kappa 1 and or kappa 2 are present, then you will have the nonlinear effects coming into prominence. Otherwise, you see, if both kappa 1 and kappa 2 are 0, epsilon n itself, there is a 0 column matrix, and these two terms will not contribute anything to the one-dimensional strain energy density. And this is very easy to observe in a thin strip, but the thin strip results are the most complicated. If you look at the results for any other type of cross-section, be it a thin-walled open cross-section or closed cross-section or solid cross-sections, you will not have this many nonlinearities. The reason is that you can think of the strip as kind of an interface between solid open cross-sections on the one hand and the thin-walled closed cross-sections on the other hand. So it kind of has the complications of both coming into picture. Of course, in terms of the analysis itself, it might look very simple because it's a simple geometry, but the end results that you look at are much more complex for a strip than they are for even an I section or channel section or a circular tube or a rectangular box beam. All those results are much more simpler than what you see over here, the kind of high level of nonlinearity which exists. The reason is basically because of the fact that kappa 1 and kappa 2 in general can be large. Next, for the same thing, that is closed form analytical solutions can also be obtained and have been obtained for open section beams, which can be thought of as made out of components, each of which is a strip. Like for example, I section can be thought of as made out of 3 strips, 2 being the flanges and 1 being the wear. Similarly, a channel section or a T section, etc. So in all such situations, you will see that the asymptotically correct first order solution basically takes this particular form. Once again, S is a matrix of constants, but now you see that, of course, we have this kappa 1 prime, which is a restrained warping effect, which we talked about earlier, but there is also a nonlinear effect that you see here through this kappa 1 squared. A thin-walled open section, unlike a strip, has the same amount of bending curvatures, order of magnitude of bending curvatures in both directions, because the stiffness are of the same order of magnitude, be it a T section or a I section or whatever. So there is no order of magnitude difference between the bending curvatures in both directions, because there is no order of magnitude difference in the bending stiffnesses in the 2 directions. So what basically happens is that the only thing that is small in terms of the diagonal elements of the stiffness matrix is the GJ, or the torsional stiffness, or GJ equivalent for a composite material. So the torsional curvatures are large, and therefore the nonlinearity is due to the torsional curvature, and of course their cross connection with any of the other 1D strains becomes dominant. And therefore you see the only nonlinear effect is basically because of kappa 1, and of course that kappa 1 squared, depending upon the actual layup you have in the composite, can link with any one of these as well as with kappa 1 prime, and therefore you get a large number of non-classical effects, but still it is not as large as what you would see here. But there is a complication here which is not present here, that is in terms of the restrained warping effect. That restrained warping effect is not important at the first order approximation in a strip, whereas it is important in an open cross section, as you see here. This as far as closed form analytical solutions to nonlinear cross-sectional analysis is concerned. Now let's, in the next slide, focus on how the same thing is handled by the code VAPs in terms of a finite element kind of an implementation. Yes, please.
So for strips, that whatever I said, that we can get more nonlinearities as compared to the thick sections. in thick sections, obviously, okay, kappa 1, kappa 2 curvatures may be less because of thickness, bending curvatures, kappa 2 or kappa 3. But there may be shear couplings may be there because of shears.
Yeah.
Deformation may be
The
large.
couplings will be there. The couplings will be there, but they are not non-linear.
How? So why
See, non-linearity happens if and only if some of the deformations are very large. Once you increase the plate thickness of a plate or a thickness of a beam, it becomes stiffer, and therefore the curvatures that it can have before failure are fairly small. Okay, so we will come into the actual mathematics of it shortly, but basically you see that the strain itself is proportional to the curvature times the distance from the neutral axis. So for example, if I am bending this, the strain at any particular location here, suppose it's just an isotropic prismatic beam and there's no coupling and its principal axis that on which I'm applying these bending moments. Let's say if I apply like this, then it has a certain curvature. Because it's a pure bending moment, it has the same curvature throughout. And now, if I want to determine the strain at any location, I have to determine the neutral axis, which of course for the symmetric section is at the center. And so basically it's the distance from the center, right? So the strain is now proportional to the curvature into the distance from the neutral axis, okay? Now the strain is limited by the material failure, okay? So that is purely a material property, and that comes as an input for us in the problem because we have chosen the material that we want to use for a particular beam. So it's of the order of, let's say, a few percentages. Since that is fixed, now your curvature gets fixed by that because your strain epsilon is of the order of basically let's say the maximum strain that you basically get is basically your gamma 11 in this particular case because it is bending. So your bending strain, the maximum that it can take is the material failure value, order epsilon, okay, which in turn is basically related to your curvature, which in this case the curvature that I was talking about here is basically curvature about the x2 axis. So it's basically kappa 2, right? So this is basically nothing but a kappa 2 into basically the coordinate along this particular direction, which in this case is basically x2, right? Oh, sorry. Yeah, it's kappa 3 into x2. Okay, so kappa 3 into x2. This is the order of magnitude. Now this is of the order of the width, which is b, right? And so now from this, basically your order of kappa 3 gets fixed as epsilon divided by b. On the other hand, for this same strip, what will happen is your kappa 2 will be of the order of epsilon by h, right? So basically I'm bending it in this particular direction. Once again, it is limited by material failure, which is the same value. So the order of magnitude is also the same, but the actual strain, 3D strain which develops, is now equal to your kappa 2, which is the bending curvature, times the distance from the neutral axis, which is now x3. Okay, and your x3 is of the order of h, and therefore this becomes epsilon by h. Okay, so now if you compare these two, you have the same thing in the numerator, but you have a larger number in the denominator here compared to this, because h is small compared to v, the thickness is small compared to the breadth. So what happens is this is going to be much larger, your kappa 2 is going to be much larger. So if kappa 2 is going to be much larger, even powers of kappa 2 will contribute the same amount of higher powers of kappa 2 will contribute the same amount as the linear terms. So that's the basic idea, and that's how the nonlinearity comes into picture. If it were all small, then only the quadratic terms will be there in the energy. But if you have higher values for these things, as is in the case here with kappa 2, then a kappa 2 cube might also contribute to the energy as much as a kappa 2 squared term contributes. That's why it basically comes into picture earlier than it would in the case of a thicker beam where h and b would be of the same order of magnitude, right? And because it is quadratic in the energy, when you take a derivative in order to find the relationship between the resultant forces and moments with the 1D strains, that becomes linear. Because you're taking a derivative of a quadratic term, it becomes linear. But when you have higher terms, the derivative becomes non-linear. So that's the basic source of this. You have any other questions on this?
In this case, we can directly ignore the lower order terms contributed by kappa 3 in the energy expression because kappa 2 is higher. So let us go with kappa 3 only. I believe in that case we will not be able to capture kappa 3 contribution.
Exactly, yeah.
Further.
Right. See, the question is, it's basically the contributions to the energy that we are concerned with. So the contribution to the energy of this particular term would basically be your stiffness which is associated with that, which in this case, because it's a 4x4 matrix, is associated with gamma 1, kappa 1, kappa 2 and kappa 3. So this is the fourth term and this is the third term, right? So basically what you're interested in there is basically your S44 over here, and here you're interested in your S33. So in terms of the contribution to the energy, it would be 1/2 S44 times your kappa 3 squared in one case, and in the other case it would be 1/2 S33 times kappa 2 squared. So this is just the terms which would contribute to a linear theory, okay? Because the quadratic becomes linear once you take the derivative. So basically what happens here is, you know that kappa 2 is much larger, kappa 2 is larger than kappa 3. So basically it means that this particular effect is going to be much larger compared to this. But you should also take into account the difference between these, okay? So you see, this is the stiffness that you're talking about. Here you're talking about an EI33 kind of an equivalent, whereas here you're talking about an EI22 equivalent. So in terms of the contribution to the energy, they will be of the same order. So you see, one of them is increasing in the product, the other is decreasing, so that you basically have the same order of contribution to the energy. Anything else on this? So now we look at how, we have seen how this is basically handled in an analytical closed form solution. We'll see how the same thing is handled in the numerical sense. So in the finite element code VAPs, of course we'll go into a little bit of details later in the course on that, but just to show the difference between how a numerical analysis handles it with respect to how a closed form analytical solution handles it. So cross-sectional nonlinearity, as I said already, was introduced in '99 by Popescu. The U1D, which is basically the energy per unit length of the beam, is modified now to include the so-called trapeze effect-like terms calculated by VAPs, and this is calculated in a numerical sense by a numerical integration over the cross-section. So these are basically area integrations. You have to mesh the cross-section, and then basically for each element you have the stiffness, and then you assemble, and basically you are basically doing a cross-sectional analysis using finite elements. Now, without adding those terms, you already know that there are three categories of models that we are basically going to be dealing with. One is, of course, just a 4x4 model, which involves all these bar quantities. So it's basically a linear model, and this is the zeroth order approximation for all beams, whether it is a strip-like beam or you have open sections or closed sections or solid, whatever. In all the cases, this is going to be your zeroth order approximation. And this is basically a linear theory with all these S bars being constants. And so your energy is quadratic in the 1D strains, and therefore your axial force resultant as well as the torque resultant and the bending moment resultants are all going to be linear in these four measures. Of course, there is going to be, in general, a full coupling. In other words, one is going to excite the other. That coupling is going to be there, but all these are constant. So that is the simplest model that you can get, and it is a model which is valid for all classes of beams. Next, when you want to refine it, go to the next better approximation. There are two ways in which it goes depending upon the type of the cross section, and this is something which will help us to classify the beam cross sections, as we shall see in today's class itself a little later. But the basic is with 4 one-dimensional strains, that are these 4, and it is valid for all classes. Once we go to the first order approximation, there are two options. One is basically you have a refined model where restrained warping effects come into picture, and that automatically comes for thin-walled open cross-section beams. And there you see that the only difference is basically this row and this particular column, which are both associated with the kappa 1 prime, which is basically a restrained warping kind of an effect. which is as opposed to an internal warping, the difference between which we discussed in the previous class. The other case is where you don't have a closed cross section. In such situations, you will have a refined theory which does not take restrained warping into account, because that is not important. Instead, it takes into account transverse shear and introduces the second and third rows in between what was already there over here. So other than these four, we are now introducing 2 rows and 2 columns which are associated with transverse shear measures gamma 12 and gamma 13. And this is basically that, remember, physically speaking, it is the difference in rotation between the reference cross section and the reference curve itself. So in other words, there is a rigid body motion where both of them go together, and then there is a further change, and it is that change which we are associating with gamma 12 in one direction and gamma 13 in the other direction. So it's basically that effect, and that becomes predominant only for solid and closed cross sections, not for thin cross sections. Next, over and above this, so all these are linear models, be it this model, 4x4 model, this 5x5 model, or this 6x6 model. Here we are talking about all of these S's or S hats or S bar quantities all being constants determined purely from the material distribution, the material properties, and the geometry of the cross section. Now when we have in specific cases the nonlinear effects becoming important, either because one of these curvatures or more of these curvatures are typically large, either because the torsional stiffness is low or because the bending stiffness in one of the directions is low. In such situations, the variation asymptotic method has to go one step further, and then it has to introduce in the next order of approximation the nonlinear terms. So these nonlinear terms, as you see, you don't have in between now a matrix of constants, but a matrix which is linear in the 1D strains. It is linear in gamma 11, kappa 1, kappa 2, and kappa 3, where A, B, C, and D are 4x4 matrices, and each one of them consists of constant terms. Of course, they can be fully coupled in general, but nonetheless fully populated in general, making all kinds of couplings possible. But you have only linear terms in the matrix itself, and then because you have quadratic because of this, in the terms of the contribution to the energy, it becomes cubic. Okay, whereas you saw in the previous slide, we can go up to quartic, even quartic terms for even with a closed form analytical solution if the geometries are simple. By simple we mean basically it can be thought of as composed of strip-like geometries. So basically either a single strip or multiple strips to make either a T section or I section, L section, channel section, hat section, whatever. So basically our star section, cruciform, etc. In all such situations you can get closed form analytical solution even up to the quartic term. Some of those terms are indeed important. But in the finite element analysis, so far what has been implemented in WAPS, it basically takes into account the up to the cubic terms. So are there any questions on this so far?
So 0th order of the last one will be first one. If you start with the third case, 0th order of that will be the first 4 4 4 4.
Yes, in all the cases, whether it is solid cross sections, hollow cross sections, thin walled or thick walled, open cross sections or strips, in all cases this is the 0th order. The first order is what basically brings it into this, and in some cases like thin walled open cross section, this becomes important along with this. So along with the kappa 1 prime, this will come. In the case of strips, along with this in the first order approximation, this basically will come. Whereas in the case of solid and closed cross section, in the first order approximation you will get only this, you will not get this. When if you go to the second order approximation, then you will get these kinds of terms. Okay, so in other words, for solid and closed cross sections, we can show mathematically rigorously that the nonlinearities are of second order and higher importance, whereas for thin walled open sections and strips, they are of first order importance. So they are more important in these two cases they are less important in this particular case. But for all cases, this is the starting point. This is the zeroth order approximation. So there is absolutely no difference from the perspective of geometry as far as this is concerned. Okay, as far as the zeroth order approximation, simultaneously important.
These are for trapeze kind of effects.
Yeah, all of these are trapeze kind of effect, but truly speaking, trapeze effect is an extension twist nonlinear coupling. So extension twist nonlinear coupling will happen between gamma 11 and kappa 1, because gamma 11 is the extension and kappa 1 is the twist. So for example, in all of these matrices A, B, C and D, we are talking about it is the 1-2 term or 2-1 term which is important. But again, even there, these will bring in bending also into effect. So it's only A12 or A21 and B12 or B21, which is basically going to purely couple extension with twist. So strictly speaking, trapeze effect is only those terms. But trapeze effect is the more commonly observed nonlinear effect, but there are other nonlinear effects which are also important. Most of the elements of your A, B, C and D for most cross sections that you deal with will be zeros. But there will be terms other than A12 and B12 also. Okay? So those terms, depending upon a particular cross section, the geometry and also the material distribution, sometimes they might cause important effects which don't have specific names, at least as of now, but are equally important to the so-called trapeze effect. So just for our convenience of nomenclature, we just say trapeze-like effects. But basically what it means is nonlinear effects. But strictly speaking, trapeze effect should be restricted to extension twist coupling, which is basically contained in your A12 and B12.
Like thin open cross section, we include the trapeze effects. Likewise, for solid cross section, for a first order approximation, we should include the brazier effect. No, first order approximation will be only this. It's only when you go to the second order approximation that you will get nonlinear effects there. Whereas here, you get this in first order approximation itself, whether for strips or for open section thin wall. In both cases, you get this at first order itself, whereas in this case, you get second order. But there is an exception where you have a closed cross section with thin walls. In other words, your H is small, the thickness of the wall is small compared to the diameter, let's say, of a circular tube, or even a box beam where the height of the box and the width of the box are large compared to the thickness of the walls, which are the webs or the flanges. So in such situations, you will see that nonlinear effect associated with brazier, which is basically nonlinear coupling between your kappa 2 by itself, not a coupling, it's not a coupling effect at all, it is a pure effect between bending moment and the curvature which results out of it. It's a direct effect. So that will be nonlinear, and that will be equally important to your transverse shear effects as well. So that is an exceptional case in this particular category where you have a closed cross section but with thin walls. But if you have a closed cross section with thick walls or solid cross sections where there is no distinguishing factor between various dimensions in any direction that you say, then basically you will have only this in the first order. You have to go for a second order approximation to get this, but it is engineeringly irrelevant because of the fact that they are much smaller compared to the effects of even the transverse shear. So typically you don't even need that. You might get probably an improvement in accuracy of the order of 0.1% or so. So which is typically useless. So you would, for a solid cross section and thick walled closed cross sections, you will not worry about this at all. Nonlinearity is, of the cross section is not important. You would still have nonlinearity in the 1D analysis because your reference curve can have very large deformations and rotations. So that can still be happening. So you might have nonlinearities there. But as far as cross-sectional analysis is concerned, as far as the elements of the matrix are concerned, you don't need to worry about functions. You can basically deal with all basically being constants. So in other words, in a finite element kind of implementation, this particular term is of no relevance at all for solid and thick walled closed cross sections.
So here A, B, C, D matrices are 4 by 4, but like the other is we have 5 by 5 and 6 by 6.
Yeah.
Is.
Yeah.
So in that case, like gamma 12 and gamma 13 will be, we're assuming to be zero contribution.
No, it has been determined when you work out the solution that there is no coupling between them and these nonlinear terms. So, or in other words, if at all there is a coupling, it doesn't happen at this order of magnitude. Maybe you have to go for a third order approximation or a fourth order approximation to extract that. So up to this order of approximation in the energy, there is no coupling between them. So the only coupling happens between the terms which you already had in the zeroth order, not the additional term which you had in the first order either here or the terms that you have additionally here. They don't get coupled with that. And it's okay because the quantity that we are interested in, energy, is basically a scalar, and to that this whole thing is a scalar quantity to which we are adding another scalar quantity. Of course, if you want to put it in a matrix form, you can basically introduce those and put all of these nonlinearities into the matrix itself, and then you would get zero additions for those additional terms coming from this. Again, the terms over here will not be affected by the introduction of this.
So for plates, for thin plates,
Yeah.
what can you say for thin plates? Which one is the?
For thin plates, basically it is the nonlinear effects which are important. So for thin plates, you know that the bending stiffnesses are very low. The torsional stiffnesses also can be fairly low. So the nonlinear effects which will come from effects like these, in fact all these three, but of course these are 1D strains. You have equivalent kappa 11, kappa 22 as the two bending curvatures, and kappa 12 as basically the twisting curvature. So all of these can be large because the corresponding stiffnesses are low, okay, for a plate. So basically the nonlinearities which are going to come because of that are going to be much more important than any transverse shear effect for thin plates. But if you go for thicker plates, the transverse shear effect will come before the nonlinear effects come into picture, because now the bending curvatures will be fairly small, the twisting curvatures of a plate will be fairly small if it's a thick plate.
Which law will follow for those thin plates? 6 by 6. This one will follow. Miss which one?
Yeah, there of course you basically have the zeroth order approximation will be your so here we are talking about U2D, which is nothing but the energy per unit area of the plate, right? So this will have your AB BD matrix into the same vector once again. So this is basically your zeroth order approximation. So this is equivalent to, in a beam, this particular situation, okay? So now whether it is a thin plate or shell or it is a thick plate or shell, the next order approximation, this is asymptotically correct zeroth order approximation, without having to make the Kirchhoff law hypothesis like the normal remains normal to the mid surface and it doesn't change its geometry, etc. You don't need to make that. Even without making that, we can derive using the variation asymptotic method and show that this is the result, which Kirchhoff and Lau got by making those assumptions, okay? Just that those assumptions were not necessary, okay, in order to derive this. But once you go for the next higher order approximation, that is you include the next higher order terms in the energy, then depending upon whether it is a thin plate or a thick plate, you will get into picture the other effects. In the case of a thick plate, you will get into effect the 3D strains associated with the gamma 1,3 and basically gamma 2,3. Basically these are transverse shear strains, okay? So in 2D sense, you can call them as epsilon 2,3 and epsilon 1,3. So basically your epsilon alpha 3, where alpha takes on the values 1 and 2, where 1 and 2 are the directions in the plane of the plate or in the mid surface of a shell, okay? So basically associated with that, you will get those additional terms. So that is equivalent in the beam sense to basically what you have over here. That is for thick plates and thick shells. You will get the effects of these kinds of quantities. On the other hand, for thin plates and shells, you will still be able to retain this kind of a structure. In other words, the effect, the contribution to the energy of this will not be important. The reason being that in a thin plate, as you go thinner and thinner, you know that you have gamma 1,3 and gamma 2,3 on these surfaces 0. So you can't have very high strain gradients, and so you cannot have, the stresses will be approximately 0, and therefore you will have a plane stress kind of an approximation, and therefore you will not be able to get much of a contribution to the energy from those effects and their direct contribution, which is basically the epsilon alpha 3. On the other hand, as you start increasing the thickness of your plate or shell, even though these stresses have to be 0 over here, they can go to a non-zero value, and sometimes fairly large non-zero value in the intermediate. And therefore, the strains that they excite, namely this, will become important. So in the case of thin plates, what you would have is now, you would have the same structure, but now your ABBD will no longer be constants. They will be functions of rho 11, rho 22, and rho 12. Because you're in a thin plate, it can undergo very large bending curvatures and very large twisting curvatures. So those will contribute to the energy as dominant effects, and therefore in the first order approximation, what will happen is your ABBD will become functions of rho 11, rho 22, and rho 12. That is the equivalent of saying that I have to add terms like these. In other words, your energy is not having only quadratic terms, it's having cubic and quartic terms as well, or maybe higher order, don't know.
Sir, because in solid cross sections, this trapeze effect is not important. Solid cross section, trapeze is not important. Closed cross sections.
Yeah.
So it becomes a second order approximation.
That's correct.
But brazier effect might become a first order approximation.
Not in solid cross sections, but in thin-walled closed cross sections. Thin-walled closed cross sections. But in thick-walled closed cross sections and solid cross sections, even the brazier effect is not of much significance. In other words, in all of them, these effects will be there. Just as it is a question of how important is it compared to the classical terms. Okay, they might be very, very small compared to the classical terms. Again, it's all relative differences that we are talking about. In one case, they are small, but they do make a difference in terms of your end results of the order of, let's say, even up to 10%, 20%. In some cases, they might make difference only up to 1%. And in cases that you are referring to, for example, you have a solid cross section and you're talking about the brazier effect, the effect might be of as small as 0.1%. So you just don't care about it. Or in other words, in an asymptotic sense, they would appear in third or higher order approximations, not up to the first or second order approximations. Okay, so there are no further questions on this. Let's go next. As far as continuing with that, the cross-sectional nonlinearity in WAPs, we saw that it's basically by adding a particular term, which is basically consisting of cubic contributions to the one-dimensional strain energy density, or in other words, the energy per unit length. So these A, B, C, and D, as you observed in the previous slide itself, are 4x4 matrices. And not all of these cubic terms are equally significant. In other words, A, B, C, D can have a lot of zeros in their elements. All cubic terms typically are small for most of the beams, in fact. And for certain beams, few of the terms become important. And as we said, some examples of that are basically the strip and or thin-walled open cross sections. So some examples of that is, if you have an open cross section, the torsional rigidity S44, remember with the classical thing you have that S44, so you have, I think it's with the 6x6, if you look at, there it is S44 is the torsional rigidity, but in the classical thing it is basically your S22, right, S22 bar. So S22 bar or S44 is small, and therefore A22 and B12 become large, or in other words, the contribution to the energy is substantial and you cannot ignore those effects. See, I mentioned only A12 and B12, but you see that A22 is also a term which involves basically kappa 1 squared along with gamma 11. So it's once again an extension twist coupling. So not only A12 and B12, but even A22, for example, can contribute to an extension twist coupling. So that's basically what is mentioned over there. Then next, other terms. Again, there is no unique way you can express this particular thing. There are many other ways you can express it. This is just for convenience, we are putting it in this particular fashion. The same energy U and D can be obtained by reshuffling these elements in some particular way. Because, for example, the contribution of a gamma 11 into kappa 1 squared can come through many of these terms, okay? And they can be kind of divided between these. So there's nothing sacrosanct about these matrices A, B, C, D. What is sacrosanct is the U and D that you get out of it. By multiplying all of these, what is the expression you get? That has to always be the same. But how you actually manipulate these A, B, C, D, these individual terms, and which element has to get how much, etc., it's all up to you according to the convenience of your derivation or implementation of the derivation in a numerical sense. So what is really significant is in terms of the strains, the 1D strains, which couples what, up to what power, and how much it contributes to the energy. That's all that is really significant. So other terms formally of the same order, but with numerically small coefficients. So as I said, A, B, C, D can have a lot of zeros. There might be some terms which don't have zeros, but they might have coefficients, for example, 1 divided by 204,000 or something like that. So because of those coefficients, which will be very, very small, because the entire contribution to the energy might also become negligible. So that is basically what is mentioned here, especially when you are using a finite element kind of implementation. Because of the numerical integrations, etc. involved, sometimes what is exactly 0 might turn out to be as a very small number as well. So that's basically what we are referring to. In addition, you could also have terms which are not actually 0, but having denominators which are actually numerical denominators, nothing to do with the material properties and or the geometry features, but just that the expression itself contains in the denominator a very, very large number, and because of that you are basically having the energy contribution to be fairly small. Whether you include those terms or not is not going to make much of a difference. So including small terms does not affect the asymptotical exactness of the full expression, because if you leave out large terms, you are going to be in a problem. If you are having additional terms which are contributing numerically very small values, of course it's going to affect your computational efficiency, but in terms of the accuracy it's not going to make any difference at all. And when and why certain terms are large leads to classification of beams on the cross-section basis, and that's what basically we will take up next to see how the beams can be classified. So basically in a rough sense, we have already discussed this when we have been talking about thin-walled open cross-sections, strips, closed cross-sections which are thin-walled or thick-walled, and solid cross-section, etc. But we want to do it in a more formal sense, and that's what this particular study actually enables us to do. So classifying beams based on the asymptotics. Of course, beams are classified based on many other aspects as well, not only by our group of researchers, but by many others before us as well. But purely based on the asymptotics in terms of the contribution to the energy, there is a way of classifying the beams, and that's basically what we look at here. So first of all, how should beams be classed? As I said, there are many bases on which you can do this classification, but the basis here is purely asymptotics. So we discussed, of course, 6 different 1D constitutive models, 3 which are basically linear, and then whether you add the nonlinear terms or not, you basically get 3 plus 3. That is 3 linear models and 3 nonlinear models, so total of 6. So what are they? Basically, the first and the second would be either the classical and or the classical exercised with the nonlinear effect. Then the second would be the generalized Timoshenko, which is a 6 by 6 matrix involving the transverse shear elements gamma 12 and gamma 13 in addition to the classical theory. And again, that also can be exercised with or without the nonlinear effect. The case where you want to have the generalized Timoshenko along with the nonlinear effect is very rare, which is hardly used. Okay, but strictly speaking, based on the models that we have studied, we have 6 different combinations which are possible. And then again, 5th and 6th would be the generalized Vlasov, where the kappa 1 prime term, the restrained warping effect, will come into picture. Again, that can be exercised with or without the nonlinear terms, but most predominantly in the case of open cross sections, you will see that the order of magnitude of both are the same, that is the nonlinear contribution and the Vlasov or restrained warping effect contribution, that is basically the kappa 1 prime contribution, will be of the same order of magnitude and therefore have to be considered simultaneously. So when to use which model is actually dictated by the mathematics of the procedure itself, because to start with, we for the derivation process, we have not only the energy but also the identification of small parameters, and depending upon what type of beam it is, we would have identified additional small parameters over and above the cross-sectional dimension divided by the length, which is common to all, the small strain, which is common to all, unless you have hyperelastic materials, which can also be dealt with, and some of us are doing that. But in general, those are the two only small parameters that we really need for a beam. But when we have special cases like thin-walled open section beams or strip-like beams, thin strip-like beams, then you have an additional parameter coming from the thickness to width ratio, and depending on that, you might have to choose the different models, and that again follows purely from the mathematics. So this is answered by the recent work leading to beam classification, and beam classification here throughout this course will be based on asymptotic results. And by making this classification, there is also practical relevance as well as an educative importance to it, in the sense that the understanding of beam analysis becomes much clearer because of this particular classification that we are going to do. Okay, so let's go ahead with this classification. So, as I said, it's based on asymptotics, but the way we name it is also quite easy to remember, because there's a association between the name of the class of the beam as well as what it actually is. So the classification is designed to be a mnemonic. So the first class that we deal with is called class T beams, where the T stands for thin-walled open cross sections. So the T there is basically stands for thin-walled open cross section, but it does not include thin-walled closed cross section beams. So that is a category which is kind of not really figuring into any one of these, but for most practical purposes it figures into this along with the solid cross sections and thick-walled cross sections, but the Bezier effect is important there. But that's a special category we'll leave out for now. T class beams only mean thin-walled open cross-section beams, and an example of that, of course, is the I section, where you have applications again not only in aerospace engineering but in many other fields like civil engineering and mechanical engineering as well. The second category is class S beams, which are strip-like beams. So of course it involves the thin rectangular strip that we have been often talking about as an interface between open sections and closed cross sections, but it can also involve airfoil like cross sections, especially because many airfoils are thin airfoils, especially for higher speed aircraft, and the thickness to chord ratio are of the order of 10% or lesser. So basically the H by B is a small parameter. So even for airfoil like cross sections, the more appropriate classification would be strip-like beams rather than a solid cross-section beam, irrespective of how the material itself is distributed within that particular geometry. In terms of the overall geometry of the cross-section, you see that the thickness is small compared to the width, so it falls in the so-called S-class. But the classic example of the S-class beam is a thin rectangle. Again, it can have initial twist, it can have initial curvature in all the situations. That is a secondary effect, but the primary effect is in terms of the shape of the cross-section itself. Finally, you have class R beams, by which we mean all the rest, all the remaining beams, all which are neither thin-walled open cross-section nor are they strip-like beams. Anything else, rest or remaining or regular, so-called regular cross-sections that we are basically clubbing into our class beams. So they include solid cross-sections and thick-walled closed cross-sections, but as I said, the thin-walled closed cross-section is a special case which does not actually figure into any one of these. At least for the up to the 0th order approximation, of course, you can put it in the R class beams, and of course all can be put into that. Basically your 4x4 is valid for all these classes. But only when you go to the next level where the Bezier effect does become important for the thin-walled closed cross-section, so that is actually not included in any one of these. So we'll retain that as a special case. But for most practical purpose, most beams that we basically deal with are one of these three categories, T, S or R. namely thin-walled open cross-sections, strip light, or the remaining regular class of beams. So they can involve, of course, much thicker airfoils, as you see in this particular case, or you can have a rectangular cross-section with or without chamfers, for example. And of course, if you have thick-walled beams. Now, depending upon which class they are, whether they are the class R, S, or T, some of these effects become important or non-important. The first effect we'll look at is the generalized Vlasov effect, which is basically a restrained warping effect. That is, if whether kappa 1 prime contributes to the energy substantially or it does not. Okay, so you see that in the case of R class and S class, it does not contribute, and that's a surprising feature. Even for S class, even though it is thin, and even though the torsional stiffness is low, you actually see that the restrained warping, which is basically a kappa 1 prime, does not contribute substantially to the energy. And that follows purely from the derivation of the mathematics for that particular case. On the other hand, for thin-walled open cross-section beams, the kappa 1 prime or the restrained warping effect becomes really critical, especially for I section beams. It is very, very important. So that has to be included. Next, coming to nonlinear effects, of which trapeze effect is an example. So trapeze-like effects, if we talk about, again for R class beams, which are solid and thick-walled closed cross sections, you will not have nonlinear effects. Or in other words, nonlinear effects, if they are there, will be absolutely negligible, in the sense that they will hardly contribute 0.1% or lesser to the energy, and therefore to the other quantities that you might be interested in, including stresses, failure, etc. All of those will be hardly affected in those cases. Whereas the nonlinear terms are extremely important in both S class and T class. And the source of these is basically, in all the cases, the nonlinear effect is purely warping. Okay, so the warping, again, we have two kinds of terms: the out of plane warping and the in plane warping within the cross section. And as we saw in the brazier effect, for example, it is basically the in plane warping, which is basically the ovalization of an initially circular cross section, which basically causes the bending stiffness to reduce, and therefore the nonlinear effect. So similarly, in the case of the trapeze effect also, it is basically the warping, or rather the manifestation of warping in terms of local rotations which basically take place, which is large, and therefore the contribution to the energy due to those such terms becomes large. Now, in terms of 1D parameters, if you're looking at it, because these warpings will be solved for by solving certain differential equations, and when we solve those differential equations, in this case partial differential equations, so when we solve those partial differential equations in terms of x2 and x3, and we get those solutions, we will see that in terms, we can substitute that warping back into the strains and then into the energy, and then integrate it to get the energy per unit length of the beam. When we see that, then in terms of the contribution to the energy, though the original source was the warping, because the warping has been solved in terms of the 1D strains, we can identify in terms of the 1D strains, which are the 1D strains which actually cause these effects. So for example, in the R class beams, all of the kappa are of the same order. In other words, you have a solid cross section, something like this. So when you have a solid cross section like this, you see that the bending stiffness about this direction or this direction, as well as the torsional stiffness, are all of the same order of magnitude. Of course, numerically they will be different, but in terms of orders of magnitude, they would be the same. None of them is very small compared to the others. So basically, the curvatures that you can get in terms of bending curvatures or the twist per unit length, which is also a kind of curvature, will all be of the same order of magnitude. So because of that, you basically see that there is no effect which is coming either from Vlasov or restrained warping or the nonlinear effects. On the other hand, in S-class beams, as I already demonstrated to you, you can have this curvature very large and the twist per unit length very large, whereas this is going to be small. Because of that, one bending measure is smaller than the other kappa I, and that's basically what you see. But of course, the torsional curvature can also be large. The next situation is where you have thin-walled open cross-section. Torsion is larger than either of the bending measures. For example, an I-section beam, of course, you would have a difference in bending stiffness in the two directions, but not an order of magnitude difference in the bending stiffness. And that's why you basically see that in terms of bending, there's not too much of a difference. One bending curvature is not much larger or much smaller compared to the other bending curvature, whereas the torsional curvatures can be fairly large if it's subjected to torque, which can go all the way up to the failure of the material. So you can have very large kappa 1s there, and therefore the effect will be pronounced, and so it becomes a fairly complex situation that you have there. So in that sense, if you are classifying it like this and looking at restrained warping effects and or nonlinear effects, you would see that the D-class beams are most difficult to deal with because both of these effects are there. But the fact remains that the number of terms that you have here in the strip-like beams is much, much larger compared to what you have here. It's only kappa 1 squared term which contributes here, whereas you can have kappa 1 squared, kappa 2 squared. Ramesh Gupta's thesis was also based on that. So if you have differences in order of magnitude differences in the material properties in different directions, that can be taken into account as small parameters as well. But most of what we will do in the whole course will not deal with that as a small parameter, because typically the way composite structures are also designed is that, for example, you have cross-ply kind of a layup, then you will have this balanced cross-ply. You will have, in terms of the overall laminate itself, same order of magnitude stiffness in the two directions. Though within each ply individually, you will have order of magnitude differences along the fiber direction and perpendicular to the fiber direction. So when we say class T beams, we basically refer to any thin-walled open cross-section beam, irrespective of how the composite construction is, or isotropic being a special case. So examples would be, other than I, channel sections, Z kind of a section, T section, hat sections, which are all commonly used. Okay, applications of course are built-up plate girders for buildings and bridges in civil engineering, heavy machinery in the case of mechanical engineering. Again, aerospace engineering, you could have aircraft stringers, spars, helicopter bearingless rotor flex beams. All of these situations have to be modeled as class T beams. The wall thickness is of order H over here. That is basically either the thickness of the flange or of the web in this particular geometry. Then the main characteristic length of the cross section itself is of order of A. So of course here I've shown the height to be A and the width to be B, but numerically though they might be different, they are not different in terms of an order of magnitude. So both we are representing as order of magnitude of A. Then the maximum strain before material failure is a fixed value, which is order of epsilon, okay? Epsilon being the failure limit, so it typically is of the order of a few percentage points depending upon the material. Now if we consider a torque M1 which is applied to such an open cross section, the way the torque is resisted, as you know from basic structural mechanics courses, is by a shear flow which takes place in all of these walls. And this shear flow, in the case of a closed cross section, can go around, whereas in the case of an open cross section, at the end of a strip, it has to turn around itself. So in other words, in the same strip, for example, if I apply torque to this, it has to be resisted by shear, of course, and any cross section, if I cut it here, because of the torque that I'm applying, there is going to be a shear which is there, and the shear in the upper portions will be in one direction, and the shear in the lower portion will be in the other direction, basically in the opposite way to resist the torque that basically that I am applying. So what it basically means is that the shear flow is turning around itself. So in other words, the effect of that has to, of course, overall match the torque that I'm applying. So in other words, it is the magnitude of that shear flow multiplied by the distance between the directions in which it is basically operating. Is the moment arm that shear flow has, is basically what is of consequence there. So if you consider a torque M1 in a thin-walled open cross-section beam, the resisting shear flow turns around at each wall edge. So for example, in the I section that we had over there, so if I am applying a torque like this, it has to be resisted by a shear flow, so there will be a shear flow something like this in each one of these. So, and overall the contribution T1, T2 and T3 should sum up to the total torque that basically I am applying in a numerical sense. So that's basically what is happening. So what we are saying is that around the wall edges, either here or you're talking about here, it's basically turning around. So that's the effect that we're talking about here. So resisting shear flow turns around at each wall edge, and this in turn implies that the maximum strain induced has to be basically that moment arm which you have to have, and in terms of order of magnitude, that moment arm has to be of the wall thickness, which is basically H. So you have a twist per unit length, which is basically an overall beam cross-section properties. The entire beam cross-section of the entire I section is rotating as if it were a rigid body. Over and above that, of course, it has the warping. So forget that for now. So basically what we're talking about is that shear flow which is there, the moment arm that it has is of the order of magnitude of H, and therefore the maximum strain which is induced by that is H times kappa 1, which is the twist per unit length, which in turn means that we already said that the maximum strain is of the order of epsilon. So this epsilon is related to this H kappa 1. It's a similar kind of exercise that we did over here. We know that the maximum strain is this in the case of bending. We know that basically each one of the, and that is in turn equal to this, because gamma 11 contribution from bending is basically this, and then we know the order of magnitude of this, therefore we can get the order of magnitude of this as this divided by this. So that's same thing is done here for torsion in the case of an open cross section, and you basically say that epsilon and H kappa 1 are of the same order of magnitude, and therefore we can now determine the order of magnitude of kappa 1 as epsilon divided by H. So the maximum twisting curvature that an open cross-section beam can have is of the order of magnitude of epsilon by H, where epsilon is the order of magnitude of the failure strain that is there, and basically H is the order of magnitude of the wall thickness. Next example in the same case for thin-walled open cross-section, if you consider a bending moment m alpha, where alpha takes on the value 2 and 3. In the case of plates, we say alpha takes on, or any Greek letter takes on the value 1, 2. So don't get confused with that. Whereas in the case of beams, always when we say any Greek subscript, unless and until we say anything else, it takes on the value 2 and 3, which are associated with the cross-sectional direction. In the case of a strip, the x2 direction will be along the width, and x3 will be along the thickness. So in the I section, for example, we can take x2 parallel to the flange and x3 parallel to the web. So basically they are cross-sectional directions, and therefore the bending moments are also about those directions. So your M2 and M3, resulting axial strain is proportional to the distance from the neutral axis. It's the same example that we dealt with earlier. So the maximum strain induced is therefore is of the order of magnitude of A times kappa alpha, where kappa alpha again is either kappa 2 or kappa 3, the two bending curvatures associated directly with M2 and M3 application. So now the maximum strain induced is the distance from the neutral axis times that curvature. So that's basically order of magnitude A times kappa alpha. So this again should be equal to, because it's the maximum strain induced, we can go only up to material failure. So this, the maximum that it can take is basically this, which is the strain at material failure. So once again, by relating these two, I can get the order of magnitude of kappa alpha as epsilon divided by A. So the maximum bending curvature kappa alpha is of the order of magnitude epsilon divided by A. Now you basically see a difference between these two. Kappa 1 is of the order of epsilon by H, whereas your other two kappas, namely kappa 2 and kappa 3, are of the order of epsilon by A. The numerator is the same, but the denominator in one case is much smaller, and therefore your kappa 1 can be much larger compared to your kappa alphas. So H is very small compared to A, means that kappa 1 is much larger compared to kappa alpha, and therefore class T beams are torsionally soft. In other words, the torsional stiffness is very small. That is, your effective GJ, even if it's a composite material, you can talk about that particular stiffness which is associated with kappa 1. So basically in terms of energy contribution, it would be that thing which multiplies a half into kappa 1 squared in terms of the major contribution to the energy. So that's your GJ, and that is much lesser than either of the EI alphas, that is EI2 or EI3. So in other words, in the case of your 4x4 matrix, the classical zeroth order approximation that we have, which holds for all classes and therefore for the T class as well. Therefore, S22 bar is much smaller compared to S44 bar, because in this matrix, 22 refers to the quantity associated with this and 4 basically associated with this particular thing, which is about the thickness direction. Basically, this is the kind that we are talking about. But here, of course, we are talking of thin-walled open cross-section, not a strip. So both kappa 2 and kappa 3 are of the same order of magnitude. Next, we'll look at class S beams, which are strip-like beams. So, as I said, it can also include thin FL cross-sections, thin and long FL cross-sections. But the classic example is the rectangular cross-section, where the height h is much smaller compared to the breadth b. So applications again are high aspect ratio wings, helicopter blades, etc. Again, high aspect ratio with high speed applications, so therefore thin airfoils are important there. And like class T beams, class S beams also have two cross-sectional length scales. In other words, not all cross-sectional dimensions are of the same order of magnitude. There is a difference. So what is that difference we're talking about? Here, as I said, H and B. And so what in terms of orders of magnitude, we say order of H and order of B, and those are different orders. Class S beam is soft in torsion, of course, just like the class T beams, the same thing, no difference there. But the difference comes in bending, because bending in one direction is very different from the bending in the other direction, because bending stiffness is much lower here compared to this. So bending in one direction as well is soft. Basically this direction, the bending is very soft. So one bending stiffness, in other words, this particular bending stiffness we are talking about is much greater than this bending stiffness as well as the torsional stiffness. So torsional stiffness and the other bending stiffness. If strip dimensions are, let's say, L, B and H, in other words, the length of this strip is L, the breadth is B and the height is H. And so we have L, of course, much larger than the cross-sectional dimension. Otherwise, it would not be a beam. You have to model it as a plate, or if it is twisted or initially curved as a shell. So L, of course, has to be large for it to be a beam. In addition, you have B much larger than H. So you have in the cross-section itself two different length scales. So the strain induced by torsion, once again, going by the same argument that we had for the T-class beams, the shear flow, and therefore the shear flow has to turn around this particular strip, and therefore it has to be the moment arm that it has, the distance it has is basically h, and so h times kappa 1 is basically the order of the strain which is induced by applying a torque to this kind of a structure, a strip. And the strain induced by bending in the soft direction is once again basically h into kappa 2. So it's a curvature kappa 2 which results, which is 1 divided by the radius of curvature in this particular direction because of the bending like this, multiplied by h, because that is going to be of order of magnitude of the distance from the neutral axis. Okay, so h times kappa 2 is the strain which is going to be induced. Of course, this particular strain is a shear strain, and this particular strain is a axial strain that you have, the bending strain that you're going to have, which is basically your gamma 11. So, but if you look at the strain induced by bending in the stiffer direction, that is basically I'm trying to bend it in this direction, it has a bending curvature like this, which is basically your kappa 3, and then the distance from the neutral axis is now going to be of the order of magnitude of the width, which is basically b. So it is going to be b times kappa 3. So that is the strain which is induced by bending. Of course, both these strains contribute in terms of three-dimensional strain, they both contribute to this. In other words, it will have an x2 kappa 3 plus x3 kappa 2. Both are basically contributing to that.
Or we can take h by 2, b by 2.
Yes. We are talking of orders of
Order is same,
magnitude,
okay.
so it doesn't matter. So a factor of half doesn't matter. In reality, in terms of numerical values, what you're saying is correct. The maximum value will be the maximum distance from the neutral axis, and therefore in both cases it will be by 2. Strain order of epsilon, because once again it's the same thing that you're dealing with, the material failure, and the material failure strain is order epsilon, assuming the same materials we are dealing with as far as the S class, as far as the T class is concerned. Epsilon remains the same. It defines the upper limit in terms of the deformation, and therefore your kappa 1 and kappa 2 are of the order of magnitude epsilon by h, basically coming from these two, because I'm relating these two to epsilon. Therefore, kappa 1 becomes epsilon by h, and kappa 2 also becomes epsilon by h. And again, this also I have to relate to the same epsilon, and therefore kappa 3 becomes epsilon divided by b. So you see, and therefore there is an order of magnitude difference between kappa 1 and kappa 2 on the one hand, and kappa 3 on the other hand, kappa 1 and kappa 2 being much larger compared to kappa 3 for the material failure to happen. So I think I'll finish this and then stop. Class R beams, which are regular beams, which means the rest of the beams which are neither thin-walled open cross-sections, nor are they strip-like beams. But again, I have to make another exception which is not made in the book, which is basically that they cannot be thin-walled closed cross-sections as well, where the brazier effect is important. So in all such things which we call as the regular beams, of which examples would be something like this or something like this, basically very thick airfoils and or solid cross sections of any geometry, as long as there is no order of magnitude difference between any direction. So whichever direction I measure, either diagonally this way or vertically, horizontally, in whichever direction I measure, I should not have an order of magnitude difference. That's basically what our class beams basically deals with. So beams with thick-walled, closed cell and solid cross sections. And class R means that all beams that are neither class T nor class S. No cross-sectional length scale effects in the strains induced by both bending and twist, which is quite obvious to see. Basically, we're talking of bending in this direction or bending in this particular direction. And the torque, in all the cases, the moment arms that are there are of the same order of magnitude. There's no difference between that. So all three kappa I are of the same order, whether it is the twist per unit length kappa 1 or the two bending curvatures kappa 2 and kappa 3, they are all of the same order of magnitude, being epsilon divided by the order of magnitude of the cross-sectional dimension. So exception, of course, as I mentioned, is the thin-walled closed cell cross-section. Need not necessarily be circular, but any other shape as well, elliptic, whatever, or even box beam for that matter, as long as the walls are thin. Then the brazier effects comes into picture, especially when they have large bending moments. The non-linearity with respect to that has to be taken into account. Otherwise, these are the easiest beams to deal with because no non-linearity, no effect associated with lasso or restrained warping. But of course, if you want to deal with higher modes vibrations or higher mode stability problems for this, then you do have to include explicitly the transverse shear measures in order to see the effect. So you might have to introduce the transverse shear gamma 1,2 and gamma 1,3 and go for that 6x6 matrix for the stiffness. But of course, it still remains linear. The nonlinear effects there are absolutely unimportant. So the wall thickness slightly affects, in the case of thin-walled open section beams, the wall thickness slightly affects the order of the strain induced by bending, and that's why you have the brazier effect. The effect, of course, is through the in-plane warping, as we saw in the previous class, where for example, you start with a circular section, it ovalizes in such a way that it flattens in the direction in which it is bending, and therefore the bending moment of inertia and the bending stiffness reduce. So with this, we have completed the classification of the beams. So then we will see how VABs as well as the closed form analytical solutions apply to each of these classes in the next time we meet, and then we will look at some kinematical preliminaries, which are basically in terms of introducing the terminology associated with the kinematics, so that can then be used to develop the beam kinematics, because without that we can't go into the strain and then therefore the strain energy which is necessary in order to apply the variation.